Morning, friends. So again, while coming to the next topic, that is rotating unbalance and reciprocating unbalance in module fifth, that is force vibration. Okay, this is very important topic. In examination, they may ask you frequently this question: explain what is the importance of rotating unbalance and reciprocating unbalance. Okay, so here in this slide, in this PPT, I'm going referring this TV Goda book images. Okay, so what is the main importance? Why we need to study this rotating unbalance and reciprocating unbalance in machine component? Okay, take every machine component there in all in almost all the mechanical devices. Even if you take the that is what the engine, electrical motor, anything. Okay, so in that there will be some unbalance takes place. Okay, it is because of what the central, the CG of the shaft and the particular component should not be coincide with each other. Okay, because of that there is a chance of rotating unbalance. Okay, that leads to what that component, if the unbalance is more in any machine component, there is a chance of what vibration takes place. Okay, if the vibration takes place means again there is a next chance is what the vibration, that what the it will produce a noise. Okay, because of noise and the unbalance or vibration, the whole component going to get corrupt. Okay, so it's a rotating unbalance. So every mechanical component what having the rotor component. Okay, so that the rotating component which will be present in the machine component, that is called as rotor. Okay, so that rotor should not be coincide with the centroidal except the particular component. Okay, because of that there is a chance of producing an unbalance. Okay, so here I will explain first what do you mean, what is the importance of rotating unbalance and reciprocating unbalance. Okay, a rotating unbalance is nothing but what the rotor will be present in the machine component, that should not be that here in the rotary component the centroidal axis, that is the center of the mass. Okay, the mass present in the rotor component does not coincide with an axis of the rotation. Okay, because of this there is a chance of producing a rotating unbalance. Okay, reciprocating means in almost all the in reciprocating motion, that is either in IC engine somewhere. Okay, because of reciprocating also there is a chance of producing a unbalance. Okay, so here okay, so same I wrote here in the introduction. Okay, generally a rotating and reciprocating machinery produces a unbalanced forces due to the inertia forces of the moving masses. Okay, that inertia force nothing but what that produces because of masses, inertia force going to set up in machine component. Okay, because of that there is a chance of producing a what unbalance. Okay, so here again you are having two different types of unbalance takes place in mechanical component. First one is the rotating unbalance and second one is the reciprocating. Okay, a rotating unbalance is nothing but what, it is the uneven distribution of the masses around the axis of the rotation. Okay, so here the centroidal axis, that is the rotation, the centroidal axis of the rotor does not coincide with the particular shaft. Okay, because of that we are going to produce what the unbalance. Okay, a rotor having a mass, that is a mass or rotor is said to be out of the balance when its center of the mass, that is the center of the particular given mass, that is inertia axis, is out of the alignment within center of the rotation. Okay, that is geometrical axis. Unbalance causes the moment which gives the rotor or wobbling moment characteristic of the vibration of the rotating structure. Okay, so here I'm with we have on derivation. Explain what the rotating unbalance. Okay, so this is about the vibrating system. Here the component, here one mechanical component I am going to fix on that particular foundation. Okay, here this figure. Okay, normally what a machine having a rotor as its one of its component is going to call as what, a rotating unbalance. Okay, rotating machine. Okay, so one of the most important application of the forced vibration in the case of vibration due to the rotating unbalance. Okay, so this is one of the most important factor. Okay, so almost this what the unbalance, it is because of what the all the manufacturer rotors have some what eccentricity. Okay, so that is the some displacement takes place. Okay, that is some distance, initial or final displacement takes place. Okay, there is a no as of now there is no any rotor which is have a zero eccentricity. Okay, so this may due to the presence of some small defects, that is a key defects. Okay, casting, non-uniformity they manufacture. Okay, so for example even okay, so in for example this rotating unbalance may cause in a turbine, electric motor, compressor. Okay, and many more. So this is about here I given one example. A mechanical device is going to fix on this foundation. Okay, so this is what the inside that is the unbalanced masses. Okay, so here because when if you start there is a chance of producing a centrifugal forces, that is which is equal to what, m naught e omega square, that is called as centrifugal force. Okay, so this is the reference axis at both end is fixed with the help of some bearing. Okay, this spring and this damper will be going to connected, that is damping. Okay, so this is C is called as damper and this is the stiffness, that is a K. Okay, so here while rotating this machine component, the free body diagram is shown here. Okay, so this is a mass So here excitation, that is a harmonic force will be going to produce. Harmonic force nothing but what, it is in the waveform. Okay, so f naught sin omega t, this is the mass. Okay, so some displacement, that is initial displacement x. Okay, so this is the spring stiffness and damper, this is the foundation. Okay, this is the free body diagram of this. Okay, here m and m naught, is nothing but what, the m and m naught is nothing but what, that is what, here m and m naught is nothing but the non-rotating moment of vertical direction. Okay, here okay, so m and m naught, capital M is the total mass, m naught is the mass present in that particular component including this mass. Okay, so non-rotating mass of the machine, m and m naught means. Okay, so here m and m naught, dx square by dx dt square plus m naught d square dt x plus e sin omega t is equal to minus kx minus e dx by dt. How this equation has come? Okay, here this is what the equation of motion in a vertical direction. Okay, that is according to the what, the displacement position, that is m is nothing, m minus m naught is a non-rotating component. Okay, so according to the sum, that is the inertia forces is equal to external force we are going to use. Okay, so here these are the two inertia forces will be produced in the machine component. Okay, and this is an external force. Okay, so that is the damping force and spring stiffness force. This is this is spring force and this is the damping force. Okay, so but so this is called as the equation of motion in vertical direction. Okay, the moment going to take place in a vertical direction. Okay, that is again you have to resimplify this, mx double dot, okay, d square nothing but one, x double dot plus cx dot plus kx is equal to me. So external force here we are going to get the centrifugal force, that is a harmonic centrifugal force, that is m naught e omega square sin omega t. Okay, so now this expression for the forced vibration with an excitation, that is what, excitation force of amplitude, that is m naught e omega square. Okay, where e is nothing but what, the radius of rotation of the mass m naught, and this is a centrifugal force. Okay, the maximum amplitude or the steady state amplitude of the response is given by this formula already we derived. Okay, that is the maximum amplitude, x of maximum amplitude fc, that is centrifugal force divided by square root of 1 k minus total mass omega square whole square plus c omega whole square. Okay, x of maximum is equal to m naught e omega square by k and square root of this 1 minus m omega square by k whole square plus c omega by k whole square. Okay, so here centrifugal force we are going to substitute the values. Okay, fc is equal to what, m naught e omega square, that you substitute here. Okay, so now you are going to again this m, you can again you resimplify this m can be taken outside. So x, this what, m naught omega, m naught e, m going to take the outside, you are going to get what, x divided by m naught e omega which is equal to omega by omega n whole square. Okay, whole divided by square root of 1 minus omega by omega n whole square to the whole square plus 2 zeta omega by omega n whole square. Okay, again you resimplify this, again x, this m, the total mass going to top side direction, x of m divided by m naught e which is equal to omega by omega n whole square whole divided by square root of 1 minus omega by omega n square to the whole square plus 2 zeta omega by omega whole square. Okay, so now this is what the this is what the maximum amplitude which is present in the machine component. Okay, similarly the phase angle. Okay, the phase angle is given by, for the rotating unbalance, phi is equal to tan inverse of 2 zeta omega by omega n whole divided by 1 minus omega by omega n whole square. Okay, so these two equations are very important. You have to derive this equation in examination. Okay, so I will repeat here, rotating unbalance is nothing but what, so here because of the rotating component which is present in the machine component, because of this there is a chance of shifting the centroidal axis, that is the center of the axis of the mass to the it will displace some position. Okay, because of that we are going to produce an unbalance. Okay, this is a rotor. Okay, so this is rotors, this is a spring. Okay, this is a free body diagram of this. Okay, and f naught sin omega t is nothing but what, the harmonic force. This is what, harmonic force. Okay, which is present in the while rotating the component. Okay, so like this according to the this what, the Newton's second law, that is a inertia force is equal to external force, you have to write here in the vertical direction. Okay, then again you resimplify this, then you are going to get this equation. Okay, so this is about the rotating unbalance. Okay, whereas in the second case is the reciprocating unbalance. Okay, so it is also similar to the rotating unbalance. Okay, but here we are going to use some what, piston component. Okay, so this is a connecting rod, this is a crank, this is a connecting rod. Okay, so here we are going to fix this IC engine on the foundation. Okay, so when the turbine, when this I am going to, if you consider an example of a turbine or that is an IC engine. Okay, so here let m naught is the reciprocating parts and the radius of the crank e is nothing but what, this e is equal to what, the radius of the crank, and l is the length of the connecting rod. Okay, and omega t is equal to what? Angle of the crank in vertical direction. Okay, so here omega t is the angle of crank to the vertical axis, and m is the total mass of the reciprocating engine including the reciprocating parts. Okay, so normally it is similar to that rotating unbalance only. Okay, so in this the unloaded balance m naught, which is reciprocating. Okay, so which is reciprocating in the mass consists of a mass of the piston and piston pin. Okay, and connecting rod. Here the to and fro motion takes place while operating. Okay, so okay, let us consider this symbol. Okay, that is what, let m naught is equal to mass of the reciprocating parts, E is the radius of the crank, L is the length of the connecting rod, and omega t is nothing but the angle of the crank to the vertical axis. So here after rotating there is a angle will be there here. Okay, and the total mass of the reciprocating engine including the reciprocating parts. M is total mass which is present in the m naught. Okay, so here same I wrote here, when the machine is running, when if you operate that machine, the base plate of the carrying the mass m naught, that is m, experience the periodic forces. Okay, when you switch on this switcher, this will be going to rotate. Okay, that going to not rotate, it will take place what are the to and fro motion. Okay, the inertia forces present due to the mass of the reciprocating part is approximately equal to this equation. F is equal to m naught e omega square sin omega t plus e by l sin 2 omega t. Here twice of that crank length. Okay, that is the angle. So this is the centrifugal force, this is the harmonic force, this is the eccentricity, that is the displaced position, length of the connecting rod, into that is the harmonic sin 2 omega 2. Okay, 2 sin 2 omega t. So you have to write up to this if they ask in the examination, explain or write a note on rotating unbalance and reciprocating unbalance. Okay, so this is very important question. Okay, so you have to note down these equations also. Okay, this is very important. So just shortly I will brief you this. The rotating unbalance and reciprocating unbalance means the unbalance it is because of the axis, the rotating axis does not coincide with an axis of the shaft. Okay, because of that there is a chance of rotating unbalance, and reciprocating also same. Okay, both are same. Okay, here we are going to rotating part will be there, that is front to motion will be there. Okay, so I hope you understand this rotating unbalance and reciprocating unbalance concept. Okay, so I thank you very much.